Good morning, everyone, and welcome to the online masterclass on theory and practice of deep learning with Professor Amir Globerson.
Should I start?
Just one second, Professor. If I could request all of the viewers, please continue to post their question and answers throughout the class and not wait till the end of the professor's presentation. The Q&A will be conducted in the latter half of this class. The Q&A portal can be found on the left side of your screens. Please begin, Professor. Thank you.
Okay, thanks. Just let me know when I need to stop for questions, okay?
Yes, sir. After half an hour.
Sorry? Half an hour?
As you finish your presentation, sir, we will begin the Q&A, which should be around half an hour into the class. Please do begin.
So the presentation is just 30 minutes then?
Yes, sir.
Okay, well, I'll stop whenever you tell me. It's fine. Okay. Good morning, everyone. I'm Amir Globerson. I'm a professor here at Tel Aviv University. And I work on machine learning and in particular in understanding deep learning. So let's start. So today I'll give a brief intro to deep learning. I don't know exactly what your background is, so we'll just catch up on this. And then I'll talk briefly about theoretical questions in the context of deep learning, what it is that we'd like to understand. Then I'll hope to give you a brief outline of how people are thinking about these questions currently. And I'll present in particular approaches to understanding this via regularization. So I'll give a brief intro to regularization and then say how that is related to deep learning in particular. So I'll gloss over a lot of technical details, and if you have questions, you can ask me later. Okay, so what's artificial intelligence, which is one of the main goals of modern technology, is to build machines that have human skills. And we have a proof of concept for this task, of course. We have our own brains that can do these things. And there's a very natural approach then to artificial intelligence, namely to build machines that are inspired by the neural networks in our brains. When these artificial networks would look something like this, they're quite far from actual biological brains, but are inspired by certain design principles in the brain. If you want to get technical and the dry truth about deep learning, about artificial neural networks, is that they are basically nonlinear functions, complex nonlinear functions with many parameters that are used to fit data. So this is sort of the dry technical explanation of what deep learning is. But it's been a tremendously important technology in, I'd say, the last 10 years or so in particular. And to acknowledge this, the Turing Award, which is sort of the Nobel Prize for computer science, was awarded to these three gentlemen, Benjo, Hinton, and LeCun, who were all involved in developing this technology. Okay, and we wouldn't be here if talking about this if this wasn't really very successful empirically. And there are many success stories of things that this technology has enabled. For example, face recognition. We have now, in a sense, machines that can recognize faces better than humans. Image understanding. So, if I look at my image library and look for costumes, it will come up with many images that have costumes in it. Namely, it understands what costumes are, which is quite impressive. You probably know that machines can now beat humans in very complex games. A key example being Go, where an algorithm developed by DeepMind now beats the world champion in Go. This is also based on these technologies. And self-driving cars, which are very developed and will probably be around very soon, are also quite heavily rely on these technologies. So these are really things that work. Okay, and there's also another sort of exciting application of deep learning is that it can be used to generate images and other things that look realistic. So these images on the right-hand side of faces are actually not people that exist in reality, but made-up faces that these models came up with. And on the left-hand side, you can see how you can make up made-up images and control their content. So you want a tree here, you want to change the sky. You want to edit it in various ways, so this is stuff that you can do. You can also ask these models to generate images with some particular content, like a bird with a yellow beak, etc., as in here. And there are also other maybe somewhat worrying applications like deepfake, where you can actually generate videos of people saying and moving according to what you want. Okay, so these are all technologies enabled by deep learning. Okay, so what's the protocol for achieving these things? It's actually quite simple. So let's assume you want to build a deep learning model that will take an image as input and output what's in the image. Like, is it an image of an apple or a corn? Okay. So how do you do that? Well, again, it's quite simple actually. You collect a lot of data that has images, okay, and so you ask people to say what is in the image. So here's an image of an apple. You ask someone what's in the image, and they write it's an apple. Okay. So you collect a large data set of such images. You ask people, you pay people to annotate these images. Let's say you collected a million such images. There is a cost to, of course, collecting such data, but it is possible, and there are also data sets available for these things. So that's your data set from which you train. Okay, so let's call the image X, and the correct label, namely, is it apple or corn? Let's call that Y. Then you decide on a network structure for your neural network. So the input of the network would be X, and the output is Y, the class. And the network is quite simply, if you want to abstract it, it's just a sequence of linear transformations followed by a pointwise nonlinearity. So you take your input, you multiply it by a matrix, and then you apply some nonlinearity to the vector that you got, and you keep repeating this until you get to the output. In terms of the nonlinearity, the most popular one is currently this function with two linear components, which is often known as a ReLU function, a rectified linear unit. So that's what almost everyone uses, and it works quite well in practice. And so once you have this architecture, this neural network has a lot of parameters. Namely, these are the parameters of your linear transformations, and your goal is to find network parameters, to find these parameters that will minimize error on your training set. Namely, you want to find a network that works as well as possible on this data that you collected. So for example, if you give it this network of yours, if you show it an image of an apple, you want it to say, that's an apple. Okay? So that's basically it. I mean, that's all there is to it. I mean, there are many details under the hood, but that's conceptually the protocol. Okay, so if we want to get a little bit more formal, let's define this. So your data set is essentially a collection of pairs of x's. These are the images, and y's. These are the correct labels for these images. And your network is essentially a function from x to y. Right? You want a function from the input to the label. And this network, or this function, has parameters, which we will denote by theta here. And theta is actually a very high-dimensional vector. So your network can have millions, many millions of parameters that you need to tune. Okay? So now we need to define a loss function that says if your network made a certain prediction, and the correct label was y, how much do you pay? So a natural way to capture this is to say, well, for example, if your network predicted apple and the true label was corn, then you pay, let's say, 1 point loss. But there are many other variants of this. So you have some loss function that measures how well you did. And then, since you have a large data set, you want to measure the loss over your entire data set. So you would sum over all the points in your data set, and for each point ask, how well did I do on this point? And then just sum all the losses. So that's the idea. And now you have what we call an optimization problem. Namely, you have this function, L of theta, which measures how well your network with parameters theta did on your training data. And you want to find the network parameters that minimize this loss, right? Because this is the network that has the best performance on your training data. So this is what we call an optimization problem. And there are many different types of optimization problem, but it turns out that there's one specific optimization algorithm known as stochastic gradient descent, which is like the magic workhorse of deep learning. It's something that works very well, and I'll talk a bit about this later. And it turns out that it's very important that we use this algorithm, not other algorithms. So let me just tell you very quickly what that algorithm is. Stochastic gradient descent. So our goal, recall our goal is to minimize this loss function, L of theta, which is the sum over our loss functions for each of the training points. So if you have 1,000 images, then this function would be the sum of the losses for your 1,000 images. So how well did your network do on the first image, plus how well did it do on the second image, etc. Okay, so this is, we'd like to find parameters that minimize this function. And here's a very simple idea, and this is essentially what stochastic gradient descent, or SGD, does. It says do the following. Take your data set of, say, 1,000 points. Now, at each point in the algorithm, choose a particular image from this data set. Let's say the image number 720, okay? Just take that image and update your model to do well on this image, okay? So the idea is you pick some image. So let's say J is this index that you picked. Let's say it's 827. You take this image. You look at the loss for that image. You calculate the gradient of that loss with respect to your parameters. Namely, this is the direction in which you need to change your parameters in order to improve your performance on that particular image. And you take a step in that direction, a small step. So eta here is the step size, and this is the magnitude of the step that you will take. Okay, so this is very simple, and this is essentially what most deep learning optimizers do in practice. There's a little detail here that usually instead of just choosing a single point, you would choose a larger batch of points, let's say 100 points, instead of just one, and do this process for this 100 data points. But this is essentially the algorithm. So again, very simple. And there are many theoretical guarantees for what this algorithm does. And we know that if the loss that you minimize is nice, in a sense, then this will actually find the optimum for that loss. Okay. So again, let's come back to what we do in practice. In most deep learning applications, you collect large data sets. And when I say large, it can be in the millions or even billions of data points. You decide on your model, and your model is this large network that has many parameters. And again, most modern models would have many parameters, millions, again, even billions of parameters. And you optimize this network to work well on your training data. Okay, and the common cases in practice, what happens is that you find that it's fairly easy to find network parameters that make your network work well on your training data, namely achieve quite low error on your training data. And okay, so that's nice, but that's not really what you want. What you want is for your network to work well on new data, right? So if you show it an image of an apple that it's never seen before during training, you want it to say this is an apple, right? And this is, that's a completely different problem, and it's not clear that your network will be able to generalize to new apples and new images of corn, but in practice it does. I mean, otherwise this would be useless, right? So we want to give this model to a farmer to show its crops, and then for the model to recognize its crops and not the crops that we trained on. And it turns out that this works actually very well. So you put these networks out in the wild, and they they do a good job. Okay, so that's all very nice. Okay, so this is the practice of deep learning. But we really, I mean, if we don't like things that somehow happen to work, but we don't understand why. Okay, so we would really like to understand why these things work. And the weird thing is that actually, in theory, we understand very little why these things work. It's even worse because, in a sense, we understand that these things should not work. So, in theory, deep learning should not work. And let me explain why and how to, resolve this apparent contradiction. Okay, so why should it not work in practice? So the learning problem, as I said, the learning problem in deep learning, or the training problem, is to find the set of parameters that works well for your training data. And this is an optimization problem, right? Let's say you have 1 million parameters, so you need to search in a 1,000,000-dimensional space for the set of optimal parameters. And it turns out that the functions that we are trying to optimize, right, here I plot a function that's just over a 2-dimensional space, and it looks nasty. And actually, the functions that we try to optimize in deep learning, they are nasty in the same sense that this function is nasty. Namely, in the general case, we can come up with functions like this that are, from a computer science perspective, are impossible to optimize efficiently. So this optimization, this training problem that we are trying to solve, there are instances of these training problems that we don't think are solvable by any computer currently, and we don't think they will be solvable by any computer in the future. So this is what we refer to as NP-hard problems in computer science. Okay, so there are learning problems that are very hard. The obvious resolution to this apparent conflict is that the problems that we are trying to solve in deep learning, for some reason, they are not as bad as this function that I have here, but they are nicer in some sense. Okay, so the real problems that we are trying to solve are apparently not as hard as the hardest problems that one could encounter in the worst case. Okay, but this is something we should think about and understand. Obviously, what is special about these real problems that makes them easier than the hardest possible problems. The other intriguing property, and I'll talk more about this today, is the problem of overfitting. So, intuitively, if you see these 5 points here, 5 blue points here on this plot, so if I ask you to just plot a function or a line that passes through these points, there are many, many possible lines that you could pass through it, right? If I don't tell you, okay, this line should be straight or anything, there are many, many possible lines you could pass through it, okay? And since there are many possible lines, it's obvious that, if I ask you about the value of a point that's not these 5 points, it will be very hard for you to predict it, right? Because if you can just pass any function, how can you say anything informative about a new point? Okay, so this is what we call the problem of overfitting. Namely, that if you have a very complex, if you try to fit a very complex function to a relatively small set of points, it's not clear how you can generalize to new points. Okay, and this is exactly the setting that we have in deep learning, because very often what we do in practice is fit very complex networks to fairly limited training data. So you can often see cases, and I'll talk about this later, where you train on, say, 1 million points, but your model has 100 million parameters. Okay, so it's really odd that a model that has so many parameters and is trained on fairly little data can actually generalize to new things. Okay, and this is the problem of overfitting, and it's not clear at all why we can somehow overcome it. Namely, how come our models that are trained on fairly little data can generalize to data they've never seen before. Okay, so that's also a riddle that we need to understand. Okay, so these are, when I talk about theory of deep learning, these are the two key questions that I want to understand. Okay, and there's been a lot of recent work on this because people really want to understand these things. As these technologies get more and more immersed in our lives, it's really important that we understand why they happen. So we can understand when we expect them to break down. If this is the thing driving your car, you really want to understand whether it can be expected to work under new conditions, right? So it's really crucially important that we have a good theory for what's happening, so we can understand these models, which will also help us, of course, build better models. So there's been a lot of excitement around this, a lot of activity, and my group here, as well as other researchers at Tel Aviv University and elsewhere, are working on this. Okay, so to summarize the current status of things, in the 90s, I don't know, probably the audience was very young back then, but neural nets have been around since the 1950s and even before. And in particular, in the 1980s, there was a lot of excitement around neural nets. But in terms of practice, they did not work as well as other alternatives. So you could say around the 1990s, theory said these models should not work, and in practice, they didn't work as well as you'd like. And in a sense, there was agreement between theory and practice. Nowadays, these models actually work fantastically well, and the theory sort of still says they shouldn't work. Okay, so again, this is the sort of thing that has stimulated this interest in understanding these models from a theoretical perspective. So what has changed? The theory obviously hasn't changed. In modern deep learning, what a common characteristic is we have much more data and larger networks. So these questions of overfitting are much more pronounced. The architectures that we use are somewhat different. This ReLU function that I mentioned before was something that they didn't have in the 80s and is apparently very important. And the training algorithms that we use are actually not that different from what we had in the past. Okay, so this is just for a historical perspective. So let me give you, I want to focus now on this problem of overfitting, namely why is it that networks that are so large and have so many parameters manage to work well on new data. And I want to describe an experiment that was performed in a paper called Rethinking Generalization. It's a paper that made a lot of impact in our field. And it's a very simple experiment that really highlights the problem or the thing that we need to understand here. So consider this image classification problem that I talked about before, namely where you have images and you want to say what is in the image, okay? So there's an image of a ship, an image of a dog, a bird, etc. And the goal of your model is to learn to classify these things, okay? So this is your original training data. Now let's imagine you do something sort of nasty, and you take the same data, but you just shifted the labels around, okay? You just assign a random label to each image. So the image that was previously a ship, and it is an image of a ship, you say that's a dog, okay? And you just randomly sample the labels for each of the images, okay? So obviously, you can't learn anything. You can't hope to learn something that you can generalize from this set of random labels, right? Because there's just no information there. But you can still give this to the network and ask it to learn, right? So let's see what happens in practice when you do this, when you learn on these two data sets. So this was it was learned on a fairly small data set, which we call CFAR10. It only has 50,000 examples. And the network that was used to learn it was actually huge. It had millions of parameters. Okay? So here's what happened. Look at the bottom line here. This is fitting random labels. Okay? So you ask the network to fit this random data set. What happens, the first thing that happens that is quite surprising is that the network reaches a training accuracy of 100%. So if you now ask the network for this random label of the image of a ship that you told it it's a dog, and you ask it, what is this image? It will tell you it's a dog. Okay? So it managed to learn these random labels that you gave it. Okay? So it has no problem actually fitting this training data. And likewise, if you show it the real data, and you ask it to learn this data, and then you ask it what's the image of the ship, what's in the image of the ship, it'll tell you it's a ship, okay? So it manages whatever training data you gave it, it manages to perfectly fit that training data. Okay, so that says that optimization here was not a problem, which is already somewhat of a surprise. But now when you look at test accuracy, namely you give it, you now take a set of new images, okay, of ships and dogs and things like that, and you ask it, okay, what's in the image? When you train that, the model that was trained on random labels gives you an accuracy of 10%, as you would expect, because you have 10 objects, different object categories, and it just guesses, right? It has no chance of actually understanding anything new because it was trained on random labels. Whereas the model that was trained on real data actually does quite well on this test data and achieves accuracies in the order of 90%. And actually, more modern architectures can get to 97% on this data. Okay, so this says something very interesting. It says that this network is complex enough to learn anything. Okay, but somehow on the real data, on data of images, it manages to generalize, whereas on random data it doesn't generalize at all. Okay, so that's sort of odd. So this phenomenon of overfitting happens for the random labels, but it doesn't happen for real images at all. Okay, so this is something, this is something for the theoretical work on the deep learning to understand. How come this huge network manages to not overfit on when you give it real images? Okay, so this is something that we'd like to understand. All right, so I'm going to very briefly go over, some of the theoretical concepts that help us understand why these things happen, and I think we have a fairly reasonable understanding of at least what the answer should look like. So to give you the flavor of the answer, I want to focus on the problem of regression, which will be easy to present and understand. So what's the regression problem? It's to learn a mapping from an input X to a continuous output Y. So for example, let's say you have a paper, you read the paper and you want to predict how many citations will it receive in 5 years. Okay, so that's a regression problem, right? So Y is just a number. So formally you have a pair of X and Y, and you assume that there's some connection between them. So Y is some F star of X, but you don't know F star. Okay, so you would like to discover it. So how do you do it? So it's like I said before, you want to learn this mapping from X to Y, so you're going to construct some network whose input is X and its output is Y, and you will learn the parameters of this network. Okay. So how do you do this in practice? So you would like to find the network, so age, that is closest to the F star, the true function F star. Of course, you can't do that. You cannot do that because you don't have all of F star. Right? But what you do usually have in practice is pairs of data points from this function, so xi, yi. For example, you have here 5 points, okay, and you would like to reconstruct f star from these 5 points. Okay, so this is similar to what I had mentioned before. So what you do in practice is you just look for the function age that minimizes the error. Let's say in this case we measure a squared error between the prediction of the network and the real values of y. Okay, and we refer to this as the empirical risk minimization principle. Okay, so this is what you would like to do. This makes sense, right? So how well does this do? You only have, say, 5 points, but you want to learn the entire function. So how well will this do? So let's think about this for a second. So if your function class age, so let's say your class of neural nets is very expressive, let's say it has millions of parameters, then it can pass many functions through these 5 points, okay? Right, because it's very expressive. But that's actually a problem, because if it can fit these functions in so many ways, if you ask it for the value of this x value where the arrow is, the red function will give you one value, and the blue function will give you a completely different value. Okay, so in that sense, it seems hopeless that we should be able to generalize at all with this, right? So if we do regression and we have a very complex function class, why should we be able to generalize at all? Okay. So I'll skip this, but the answer is we should not expect to generalize well at all if we have a complex function class. Okay, but there's another idea, and this is much closer to what neural nets do, and it's as follows. You say, okay, among all the functions that pass through these 5 points, why don't I look for the nicest function? Okay, and the nicest can be, let's say, the smoothest function. Okay, so this is the function here in black. So, intuitively, it makes sense to return that function because there's something nice about it and we expect it to maybe generalize better, okay? So this is the idea of regularization. It's really a key concept in learning theory and learning generally, okay? Okay, so to make this a bit formal, let's say we have a function r of h that measures how nice a function is, okay? So if this function is nice, then r of h will be low, okay? So for example, a smooth function will have r of h maybe 0.001, and these highly non-smooth functions will have r of h 100, okay? So now we can define a new training goal, which is to find the function that is nicest, namely has the lowest r of h, while also fitting the data, okay? So among all the functions that fit the data, let's find the nicest one, okay? So this is an approach to learning that's a bit different from what we had before. And it says, okay, if you have many functions that fit the data, just find the nicest one, okay? Where nicest means low r of h. Okay, so you prefer a simple function that also has the correct output. Okay, so again, this is the setup for regularized learning. So let's denote the solution by age of r of this problem. So very importantly, we have a lot of theoretical results that tell us that this is a very good idea. Namely, they tell us if you do this thing of finding the simplest or nicest function, your error, your true error, will be proportional to how nice your function is. Okay, so we have results that say if you manage to find a function with low r of h, then your true error will be proportional to this r of h. Okay, and this essentially tells you that you can learn very complex function classes, but if you find you happen to find a nice function in this concept class, you will also generalize well. Okay, so this is a very key concept in learning theory. How am I on time? I guess I don't have much time left. Okay, so I'll continue until someone stops me. All right. So just to show, yes?
Yes, Professor, you can keep going. I will interrupt you when we'll have to start the question answers.
Okay.
So I think we have about 5 to 6 more minutes.
Okay, sounds good. All right. Just to show you that this is actually a very real thing, it's not just theory. So I ran this example where I gave a neural network 5 points. So these are the points in orange, okay? I gave it the x and y coordinates for these points, and I asked it, please give me the function that fits these training points. Now, you should know that this neural net, it was actually huge. It had 1,000 hidden units, okay? So it had more than 1,000 parameters that I asked it to fit just these 5 points. So you know, this network can fit wild functions that pass through these points. But the function that I actually returned is this nice smooth function, which is, I think, is amazing, right? Because somehow this network, although I didn't tell it anything about that I would like a smooth function or anything like that, it managed to find this function and not all the wild functions that could pass through these 5 points, okay? So this is really the essence. If you want to understand why deep learning works, it's this example. Namely, that there's something in the way that we train these networks that make them find these simple functions and not the other wild functions that they could in principle find, okay? So I think this really nicely illustrates the point. So this is training a huge network with many parameters on just 5 points, and this is the function that this finds, okay? So despite being very expressive, this network finds a very simple function where it could have fit much more complex functions. So why did it find this one, okay? So this is the question, and let me tell you the answer. I mean, I have more formal slides on this, but I want to give you the simple answer. So the answer is that the reason why it found this simple smooth function is because of the training algorithm that it uses. So remember before I told you that stochastic gradient descent is the algorithm that we use for finding the best network. And it turns out that stochastic gradient descent has this theoretical property that it will find these nice functions and not other functions. So if you were to use a different learning algorithm, like some other more complicated Hessian methods or interior point or anything like that, these would actually run the risk of overfitting much worse than this. Okay, so it's important when you train your deep learning models to use this precise algorithm that has this very nice property. Okay, so this is essentially the answer. So if you want to, to summarize the state of understanding deep learning theory nowadays, the explanation is that we can learn very large networks on relatively few data points and generalize because our learning algorithm, namely SGD or stochastic gradient descent, will find the nicest or in a sense smoothest function that passes through these points. And because it's a nice function, smooth function, we have theoretical guarantees that it will generalize well. Okay, so this is the essence. So I do have more slides that theoretically explain this, but in the interest of time, I will not do this in detail. Let me just say that the idea of regularization is quite old in statistical theory, in learning theory, and it's just we are now just beginning to understand how important it is in the context of deep learning. So this is Tikhonov, who was a Russian mathematician who was one of the founders of this field. You might know ridge regression in statistics. That's also a use of regularization. Kernel methods that are were the underlying technology for or theory for support vector machines that were sort of the reigning technology before deep learning. They also strongly rely on regularization. There's actually now a lot of understanding of how these things are related. So there's we're going back to understanding kernel methods in order to understand deep learning. The theoretical understanding of regularization is related to Rademacher complexity. So this is something that you should look into if you want to understand the theory. Lasso, which you might also know, is also based on regularization. And these names here, Alan Zhu, Cerebro, Sudri, Jason Lee, Sanjeev Arora, are all people working on these theoretical aspects of deep learning and generalization. So I do have more formal explanations for why this work and derivation that essentially shows. Okay, so for example, this slide, the conclusion was that we can prove is that stochastic gradient descent finds the minimum norm regressor, namely it finds the nicest or smoothest regressor among all the possible functions that can fit the data. Okay, so these are things that can be proven, and they highlight the importance of using this algorithm for training. Okay, and there are also, as I said, these things are very closely related to the notion of kernels. So I won't go into that. Yes. So okay. So are we done with these explanations? Does that tell us everything? Well, not quite. Let me tell you what does the theory tell us. It tells us that for very large networks, if you train with SGD, it will converge to a nice solution for a given notion of niceness. Okay. But there are many caveats with this theory. It still does not explain everything. For example, the networks that we train on are not that huge, not in the sense that the theory wants them to be. There are some very simple functions where this theory doesn't explain why we can learn in practice. And there are many other things. So, the story is not done. We have a good intuition for what's going on, but it's really far from really understanding the full picture. Okay, so as I said before, I just talked about overfitting here. There are still many questions about optimization, namely how is it that we manage to solve these very complex optimization problems. This is actually not as well understood as the questions of overfitting. because of these functions being potentially very ugly, like the one that I have here. There are some understood cases, like simple networks that have linear activations, matrix factorization, and huge networks where optimization is maybe better understood. There's also results from my group. You can look up papers by Alon Brutskus, who's a grad student working with me. But there's still a lot to do, so I invite you to look into this. So to conclude, there's much theory on understanding deep learning recently, but there's even more to discover. We need theory that explains realistic architectures, realistic data distributions, so what makes images, why do our models work for images, and explain why optimization algorithms that we use in practice work, okay? So I find this to be a very exciting mix of theory and practice, and I invite you all to look into this. So thank you.
Thank you, Professor. We have some questions for you.
Yes.
Before we get to the lengthy questions, there is one viewer who was requesting that if you could explain regularization a bit more, please.
Yes. So let me go back to these slides. So regularization as an idea is very simple. It says, let me go back to, you can explain all of it on this slide, okay? So let's say your training problem is you get these 5 blue points, okay? And someone asks you, give me a function that passes through these points, okay? So there are many, many possible functions. And the idea of regularization says, let's define some notion of niceness for functions. So we'll say some functions are nicer than others, okay? And let's ask the algorithm to return the nicest function that passes through these points, okay? This is the idea of regularization. So this function that measures niceness is what we call a regularizer, okay? So that's basically the idea. So regularization means that in a problem where you have many possible solutions, define some property of the solution and look for the solution that is optimal in the sense of this property. Does that make sense?
Yes, sir. Thank you. Another question that we have is, what equation would you think would fit for machines in health intelligence? Like, say, if a person is suffering from a sudden cardiac arrest, will we be able to use artificial intelligence to analyze that situation?
Yes, so there is huge the amount of activity in healthcare now with AI and machine learning methods. So basically, any setting where you want the machine to predict something or make a decision, you can cast it in these terms. So if you want to look at the EKG and say whether the person is in risk of a heart attack, that's basically a classification problem, right? So you just need to this is not an easy thing, but you need to collect data of EKG for different individuals and say, okay, that individual had a problem, that individual did not, and then you can learn these functions to make these predictions. So I think that the first step in using, say, machine learning for any application is just understanding what it is that you want the machine to do. Okay, what prediction do you want the machine to carry out? The second step is collecting data from which the machine will learn, and then all the rest is actually, is pretty, over-the-shelf technology that you can use.
Thank you. Another question is that it's widely known or perceived that the protocol to create a deep learning program or a deep learning model needs to be as accurate as possible, because apparently they are difficult to debug retroactively. Could you shed some light on exactly why are they difficult to debug?
Yeah, so I think, first I would say that the possibilities to debug these systems are improving with time. So the frameworks like PyTorch from Facebook or TensorFlow from Google have more and more options to do this. But it is true that you often find yourself training a model on millions of data points, and then there are essentially two ways a model can fail. One is that it will not fit your training data well, okay? And then, there's no hope for it to do well on testing if it's just, it has miserable accuracy on your training data. And for that, to understand why optimization fails, I think there are, different, basically, it fails because of two possible reasons. One is maybe it's just a difficult problem. I mentioned that there are difficult optimization problems, so maybe it's one of those. But actually, more often than not, it fails because there are many parameters in the training algorithm that you can tune, like step size, the exact optimization algorithm like AdaGrad or SGD, and you need to play with those. So this falls under what we call hyperparameter tuning or AutoML, and there are actually better methods now for exploring this set of hyperparameters in all frameworks. So that's something that's improved, but I think it does help to understand the theory in order to debug these methods. So for example, when you understand the theory, you understand that it's, in terms of optimization, it's actually better to use a larger model. So when students of mine tell me, okay, I tried to train this model and it failed, I tell them just use a bigger model. First, really increase the size of your network until you can get to low training error, okay? So, there are various tricks of the trade, and also, that you get from understanding these problems that help you in debugging, I would say.
Thank you. Another question, sir, is could you explain the difference between SGD and polynomial fits?
And polynomial fits?
Yes.
I would say these are two different methods, in the sense that if you want to, I assume by polynomial fitting you mean you have a set of the data points and you want to pass a polynomial through it, okay? So when you say polynomial fitting, this relates to the function class that you want to use when fitting the data. SGD is an optimization problem. So SGD can be used, say, for polynomial fitting if you want to find the best polynomial. Okay, so these are two different things.
Thank you. One question here is, do you think the methods of deep learning could be used to predict sensor failure?
Yes, certainly. I mean, this is, again, as I said before, almost the only thing that you need in order to apply these methods is just to understand what the problem is. Okay, so sensor failure is a problem where you have past readings of a sensor, okay, and maybe other features like temperature and stuff like that, and you want to predict basically a binary variable saying will this sensor fail or not in, say, a week, right? So this is a classification problem, and what you need to do is collect data, past data from your sensors, and in this data you will have cases where sensors failed and cases where they did not. Okay, so your machine can now learn to find the features of the sensors of past readings that predict that this sensor will fail. Okay, so for example, it might learn that if the sensor has irregular values at some point, then that's a good predictor for future failure. So certainly this is something you can do, and I think it's been done all over the place.
Thank you, sir. There is a question about adding exceptions to a deep learning function.
Mm-hmm.
The question is, how does an exception get introduced to the function? If the function has a relationship between x and y, but that relationship has exceptions, how does one introduce them?
Okay, that's a very good question. So I assume what you mean is, let's say you have a function that learns to classify images, let's say corn and apple, but now there's a very funny apple that it's never seen before, and you would like to say, okay, you should know that this is an apple. So there are various ways you can do this. One is to combine different learning algorithms, like say nearest neighbor and deep learning, and to have a meta algorithm that looks at a particular instance and decides whether this is an exception that you should classify with with one algorithm and not with the other. Okay, so there are, this would go under boosting or ensemble methods, which is actually something quite popular. So if you look at Kaggle or competitions in machine learning, you quite often find that the best performing systems are actually a combination of multiple existing systems. So that would, in a sense, also be a way of handling exceptions. Obviously, another approach is just to add, if you have this strange apple, that's a new apple, just add it to your training data, and most likely the network will be able to learn that this is a new class of apples that it hasn't seen before, and generalize to that as well. So that's another possibility.
Thank you, sir. A question that we have received is about, can we use more than one model for training? So, for example, can both gender recognition and emotional recognition be detected in the same model?
Very good question. Yes, so this is known as multitask learning, and you can imagine it's quite often done. So you can imagine, let's say there's an image, okay, and you want to predict for this image what is the gender of the individual and what is their facial expression, okay. So the network for this task would usually look like there's a network that takes the image as input, does a lot of processing to it, okay, and that part of the network is joint, is common to both the gender and the emotion predictors, and then at the end there will be a split where one part goes to the gender and one part goes to the expression. We call these prediction heads in learning. You might see that terminology, but certainly that's a common architecture.
All right, sir. Someone has asked if deep learning can be applied to coding, and if yes, then how?
Yeah, so I think there's quite a lot of activity around deep learning for software design, let's say, and programming languages. It's just my field, so but I've seen things like automatic generation of code. So you have something that you want to achieve, and you train a model to write code that does that. There's also the reverse, where you have code and you want the network to explain what the code does. There's stuff like the code design. There's verification that's being done with the machine learning. So again, it goes back to whatever task that you can define. Let's say you give code and you want to say, will this code work or not in this particular case? Okay, so it's a classification problem. Okay, or find me a line in this code that is dangerous. Okay, so these are all tasks that are well defined, and you can therefore train models to do those. But the short answer is yes. There's a lot of work on AI and machine learning for coding.
Thank you, sir. We have one question which is not directly related to machine learning or deep learning.
Mm-hmm.
A viewer has asked about your views on quantum computing, and if you think the role of binary coding in computers has reached its satiation.
Okay, so since it's not my field, I feel that I can't really give an informed answer. I, like all of you, I know there's a big excitement around quantum computing with Google reaching quantum supremacy reportedly. So obviously a lot of excitement there, but I'm not sufficiently an expert to give informed comment on this.
Thank you for trying those, sir. We have a couple of questions about the future of deep learning, machine learning, and AI.
Mm-hmm.
The first one is, do you think machine learning can evolve to eventually find cures for cancer or other incurable diseases?
Mm-hmm. So again, I should be, I mean, since this is not, I'm not a biologist or a computational biologist, so I'm not sufficiently informed. I don't think anyone would, would give you a completely positive answer to that, because it's hard to predict. I think these technologies carry a lot of promise in terms of the things that they can help us do for science. So, for example, there is a lot of work on using machine learning for drug design, because you can train models to find molecules that have certain desired properties. So that can bind to particular sites, and obviously that's very important in curing disease. You can also train models to help you find genes or certain molecules that are implicated in disease. So this certainly can help you in many steps of both understanding disease and designing drugs for particular diseases. There's a lot of current activity, so I'm sure it will play a role in modern and future biology and medicine and biomedicine. So yes, so it will certainly help. Whether what is the exact path of the future, I can't say.
Thank you, sir. Speaking of paths for future, the last question here is about your opinions on where deep learning, ML, and AI are heading. Mm-hmm. Where do you think it will be in the next year, since the turnaround of this evolution is getting faster? Where do you think it needs to aspire to be in another 5 years?
Okay, great question. So I think there's, as you said, that there's a huge, volume of activity, and progress is very fast. We've seen in natural language understanding in the previous years, since the introduction of models like BERT, there was a substantial jump in performance in tasks like question answering. So I think we can expect to see, improved technology for both language and images and also interactive systems. I think a huge challenge for these models is, again, interaction with humans. So, for example, dialogue is something where we're still lagging far behind what we'd like to achieve. So you don't have a machine now that you can, perform a conversation with over many turns of conversation, and it will seem, like a Turing test that this machine is human. So we're not there yet, and that seems like a serious challenge. I think, in 5-10 years, I think we'll be there's probably going to be substantial progress on this. It's hard to say whether we'll, reach something that is sufficiently human-like, but there's certainly going to be a real progress. Robotics is somewhere where I think there's a lot of room to develop better technology. We still don't have like humanoid robots that can do things even like washing dishes and folding laundry. There's some prototypes, but it's far, and I think it's fair to expect that there will be substantial improvement there as well.
That is comforting to hear, sir. To end this session, one question about the beginners, since the lecture has been about people who are already interested in deep learning and ML and AI. A viewer has asked, if someone is merely interested in these theories, how do they get started with understanding them? What would be the right path to study this?
So I think if you're interested, I guess there are two questions. One is, if you want the more practical side of learning, then I would start with frameworks like TensorFlow or PyTorch, and with simple tutorials for these. So you just need to know some Python. And I've seen people getting started on this fairly easily, and there are many challenges that you can play with and benchmarks. So that's on the practical side. On the theoretical side, I think if you Google theory of deep learning, you can find many online talks about this. I do think it's very important to take a proper introduction to machine learning course. So there are courses in many universities. There's a nice textbook that I like. It's a bit more advanced mathematically, but it's a good read by Shai Shalev Schwartz and Shai Ben David. So that's a nice textbook that I think is online as well. And yeah, there are many resources online.
Thank you, sir. With this, we come to the end of this online masterclass. Thank you, viewers, for participating in this masterclass. Thank you so much, Professor, for your time and your expertise. This has been an enlightening session. We are grateful to you and to Tel Aviv University, and we're delighted that the India-Israel partnership has grown via this exchange of knowledge, and we hope to continue with this. Thank you so much, Professor.
Okay, great, thanks. It was fun. Have a good day.